Hello there and welcome to Science with Sleepy. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and digital mysteries, rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light, as if gravity itself has softened. Because tonight, we aren't exploring space or diving into the ocean. We're diving into something invisible, something that surrounds us every moment: data, information. Digital bits and bytes flowing through cables and airwaves. Every photo you take, every video you watch, every message you send, it all becomes data. And we're creating more of it than ever before in human history. But here's the question that will guide our journey tonight. How much data would it take to paralyze the entire internet? What happens when we create too much? Could we actually fill up all the storage space? Could we break the internet itself? We'll explore how much data we're creating every second, where all this data lives, the massive buildings and cables that hold our digital world. We'll discover the limits of storage, what happens when those limits are reached. And finally, we'll explore the race to keep up, the solutions scientists are working on, and what this all means for our digital future. Some of what you hear tonight may surprise you, or at the very least spark some curiosity as you drift off to sleep. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. Picture this. Right now, as you're listening, millions of people around the world are taking photos, posting videos, sending messages, streaming shows. Every single second, humans create more data than existed in all of human history just 200 years ago. Think about that. In 1 second, we create more information than our ancestors created in centuries. Where does it all go? How much can we store? That's our first mystery to solve. But it's more than a mystery, it's a challenge, a real challenge. One that affects everyone, one that shapes our future. Every photo you've ever taken, every video you've ever watched, every message you've ever sent, it all becomes data, it all needs storage, it all takes up space, real space, physical space, in buildings, on servers, in data centers around the world. But here's the question. What happens when we run out of space, when storage fills up, when we can't store anymore? Could we actually break the internet? Could we paralyze the entire digital world? These aren't just theoretical questions, they're real questions. Questions scientists are asking, questions engineers are working on, questions that matter, questions we need to answer. So tonight, we'll explore this digital mystery. We'll discover how much data we're creating, where it all lives, what the limits are, what happens when we reach them, and most importantly, what we can do about it. Because this isn't just about technology, it's about our future, our digital future, a future we're all creating, together, one byte at a time. Chapter 1: The Data Explosion. How much are we actually creating? Every second, humans create data, lots of it, more than you can imagine. More than seems possible, but it's true. We're in the middle of a data explosion, an explosion that's getting bigger every single day. Let's start with something simple. Photos. You've probably taken photos today. Maybe with your phone. Maybe you posted one online. That photo becomes data. Digital information stored somewhere. A single photo from a modern phone might be 5 megabytes. That doesn't sound like much, But multiply that by billions. Billions of photos. Every day. The numbers become enormous. Now imagine everyone doing that. All at once. All around the world. Billions of people. Each taking photos. Each creating data. The scale is mind-boggling. Let me give you a comparison. In the year 2000, digital cameras were new. Most people still used film. The total number of photos taken that year was maybe 80 billion. Worldwide. For the entire year. Today, people take that many photos in about 2 months. 2 months. What took a year now takes 2 months. And the rate keeps accelerating, getting faster, every year. Think about your own photo collection. How many photos do you have on your phone? Maybe hundreds. Maybe thousands. Now imagine everyone has that many. Billions of people. Each with thousands of photos. The total becomes astronomical. Here's a number that might surprise you. Every single minute, people upload about 65,000 photos to Instagram alone. That's just one app. One website. In 1 minute. Think about that. 65,000 photos. In 60 seconds. That's more than 1,000 photos per second. Just on Instagram. But Instagram isn't alone. Facebook sees millions of photos uploaded every day. TikTok videos flood in constantly. YouTube receives hundreds of hours of video every single minute. Every click, every search, every message, it all becomes data. Let me tell you a story. Imagine a person. Let's call them Alex. Alex wakes up in the morning. They check their phone. That creates data. They take a photo of their breakfast. More data. They send a message to a friend. Even more data. They watch a video. Stream music. Scroll through social media. By the end of the day, Alex has created thousands of pieces of data, hundreds of photos, dozens of videos, countless messages. Now multiply Alex by billions. Billions of people, all creating data, every single day. The numbers become mind-boggling. Impossible to grasp. But here's something even more amazing. All the data created by one person today might equal more than all the data in entire libraries from just 100 years ago. Think about that. One person. One day. More information than entire libraries full of books. That's how much data we're creating. Let's think about it like water. Imagine data is water. Each photo is a drop. Each video is a cup. Each message is a tiny splash. Now imagine billions of people, all adding drops and cups and splashes. Every second, every minute, every hour. The bathtub fills up fast. But what if the bathtub is the internet? How big is that bathtub? Can it overflow? Now let's talk about videos. Videos are huge. They take up way more space than photos. A single minute of video might be hundreds of times larger than a photo. And we're creating videos constantly. YouTube receives about 500 hours of video every single minute. That's 500 hours. In 1 minute, think about watching all that video. It would take you 500 hours. That's more than 20 days of non-stop watching. And that's just what gets uploaded in 1 minute. One tiny minute. TikTok sees billions of videos created every year. Each video might be 15 seconds long. But multiply that by billions. The total becomes enormous. And people watch these videos constantly. Billions of views every day. Each view creates data. Each interaction creates data. It all adds up. Netflix streams millions of hours of content daily. Think about that. Millions of hours. Every single day. And that's just one streaming service. There are many others. Amazon Prime, Disney Plus, Hulu, all streaming content. All creating data. Every time someone watches something, that creates data too. Not just the video itself. but the record that someone watched it, when they watched it, how long they watched, where they paused, what they skipped, all of that becomes data. Netflix tracks what you watch, when you watch it, how much you watch. They use this data to recommend other shows, to decide what to produce, to understand what people like. All of that requires storage. All of that becomes data. Let me give you a specific example. A single hour of high-definition video might be 3 gigabytes. That's 1 hour, one show. Now imagine millions of people watching millions of hours. The data becomes astronomical, impossible to comprehend. Here's a story that shows how big this gets. In 2012, a video called Gangnam Style went viral. It became the first YouTube video to reach 1 billion views. That's billion with a B. Think about all the data that created. Not just the video file itself, but every view, every comment, every share, every time someone watched it. All of that became data stored somewhere. The video itself was about 50 megabytes. That's the file size. But the data created by views was much larger. Each view created a record, a log entry, metadata, all stored, all taking up space. By the time it reached 1 billion views, the total data created was enormous. Not just the video, but all the records, all the metadata, all the interactions. It all became data. It all needed storage. Today, videos reach billions of views regularly. Some reach tens of billions. Baby Shark has over 13 billion views. Think about the data that created. The video file, plus 13 billion view records, plus comments, plus shares, plus likes. The total is mind-boggling. And it's not just popular videos. Every video creates data. Every view creates data. Every interaction creates data. It all adds up. It all needs storage. It all matters. Today, videos reach billions of views regularly. Some reach tens of billions. Each view creates data. Each comment creates data. Each share creates data. The numbers become astronomical. But here's something you might not know. There's data you're creating that you don't even know about. Hidden data. Background data. Data that flows constantly without you noticing. Every time you open an app, it creates data. Every time you search for something, that search becomes data. Every time your phone checks for updates, that creates data. Your smart devices are constantly talking to the internet, sending information, receiving information. All of it becomes data. Think about smart home devices. A smart speaker listening for commands. A smart thermostat adjusting temperature. A smart doorbell watching for visitors. All of these devices are constantly connected, constantly sending data, even when you're not using them. The Internet of Things. That's what scientists call it. All these connected devices. There are billions of them. Billions of devices, all creating data, all the time, day and night. Whether you're awake or asleep. Here's a number that might blow your mind. By some estimates, there are more connected devices in the world than there are people. Way more. And each device creates data, constantly, every second of every day. Let me give you some examples. A smart thermostat might send temperature data every few minutes. A smart doorbell might send video when someone rings it. A smart refrigerator might track what's inside. A smart car might send location data constantly. Each device creates small amounts of data, but multiply that by billions, billions of devices, all sending data. All the time, the total becomes enormous. It all needs storage, it all takes up space. And these devices are multiplying. Every year, more devices get connected. More things become smart. More data gets created. The growth is accelerating. The data explosion is getting bigger, faster, unstoppable. So we have photos, videos, messages, app usage, smart devices, all creating data. But how much, really? How much data are we creating? Let's talk about the units. Data is measured in bytes. A byte is like a letter, one letter in a word. But we create so much data that we need bigger units. Much bigger. A kilobyte is about 1,000 bytes. Like a short paragraph. A megabyte is about 1,000,000 bytes. Like a short book. A gigabyte is about 1,000,000,000 bytes. Like a small library. A terabyte is about 1,000,000,000,000 bytes. Like a huge library. But we create so much data that we need even bigger units. A petabyte is about 1,000,000,000,000 bytes. That's a 1 followed by 15 zeros. An exabyte is even bigger. A zettabyte is mind-bogglingly huge. Here's a comparison that might help. If you printed out 1 terabyte of data, it would create a stack of paper taller than Mount Everest. 1 terabyte. Now imagine zettabytes. The numbers become impossible to visualize. Scientists estimate that humans create about 2.5 quintillion bytes of data every single day. That's 2.5 followed by 18 zeros. Every day. Think about that. Every single day, we create more data than existed in all of human history until very recently. To put that in perspective, if you tried to store that much data on DVDs, you'd need a stack of DVDs reaching from Earth to the Moon and back twice. That's how much data we create every single day. The growth is exponential. That means it's not just growing, it's growing faster and faster. Like a snowball rolling downhill, it starts small, but as it rolls, it picks up speed, it gets bigger, it moves faster, it becomes unstoppable. In 2010, humans created about 1.2 zettabytes of data for the entire year. By 2020, we were creating that much data in just a few months. The acceleration is incredible, the growth is unstoppable, at least it seems that way. But here's the key question: can storage keep up? Can we build storage fast enough? Can we store all this data? Or will we hit limits? Will we reach the breaking point? That's what we need to understand, that's what we need to solve. That's what's happening with data. We're creating more every year, and the rate keeps increasing. What took a year to create might now take a month. What took a month might now take a day. The acceleration is incredible. But here's the key question: where does all this data go? How much can we actually store? That's what we'll explore next. Because creating data is one thing, storing it is another. And storage has limits. Real limits. Physical limits. Limits we're racing toward faster than ever before. Let me tell you another story. This one about a single day. Just one day. In 2020, humans created about 2.5 quintillion bytes of data. That's 2.5 followed by 18 zeros. In one day. Now imagine that every day. Day after day. Year after year. The numbers become impossible to comprehend. But here's what makes it even more incredible. That number keeps growing. Every year, we create more data than the year before. The rate of growth is accelerating. It's not linear, it's exponential, like a rocket taking off, getting faster and faster, going higher and higher. Think about your own data creation. When you were younger, maybe you took a few photos, maybe you sent a few messages, but today, you probably create data constantly. Without even thinking about it, every app you open, every website you visit, every video you watch, it all creates data. Now multiply that by billions. Billions of people, all creating data, all the time. The scale is mind-boggling. The growth is unstoppable. At least it seems that way. But here's something to think about. All this data has to go somewhere. It can't just disappear, it can't just vanish. It needs storage. Real storage. Physical storage. And storage, as we'll discover, has limits. Real limits. Physical limits. Limits we're racing toward faster than ever before. So remember this. We're creating data at an incredible rate, faster than ever before. And that rate keeps accelerating. Every photo, every video, every message, every click, it all adds up. It all becomes data. Data that needs somewhere to live. Data that needs storage. And storage, as we'll discover, has boundaries. Chapter 2. Where does all this data live? The hidden infrastructure. The internet isn't magic. It might seem like it sometimes. You tap your phone, a video appears. You send a message, it arrives instantly. It feels like magic, but it's not. It's physical, real, made of buildings and cables and machines. All that data we're creating, it has to live somewhere. It can't just float in the air. It needs physical space, real storage, actual machines. And those machines live in places called data centers. Picture a data center. Imagine the biggest warehouse you've ever seen. Now make it bigger, much bigger. Now fill it with row after row of computers. Thousands of them. Maybe tens of thousands. All humming, all storing data, all connected to the internet. That's a data center, a massive building filled with servers. Servers are just computers designed to store and share data. But these aren't like your laptop. These are powerful machines, built to run constantly, day and night, never stopping. Let me tell you a story about visiting a data center. Imagine walking into one. The first thing you notice is the sound, a constant hum. The sound of thousands of computers running, all at once. It's like standing inside a beehive. But instead of bees, it's servers. Instead of honey, it's data. The sound is constant, never stopping, day and night, week after week, year after year. The servers never sleep, they never rest, they just run, constantly, storing data, processing requests, keeping the internet alive. The sound is also loud, really loud, like standing next to a highway, but instead of cars, it's computers. Thousands of them, all humming, all working, all creating that constant noise. Workers in data centers often wear ear protection, like construction workers. Because the noise is that loud, that constant, that overwhelming. It's not a quiet place. It's a place of constant activity, constant work, constant data. The second thing you notice is the cold. Data centers are freezing. Why? Because all those computers generate heat. Lots of heat. If they get too hot, they break. So data centers have massive cooling systems, air conditioning on a huge scale, keeping everything cool, keeping everything running. The third thing you notice is the security. Data centers are like fortresses, cameras everywhere, guards, locks, biometric scanners. You can't just walk in. These places protect something valuable, your data, everyone's data. Inside, you see rows and rows of servers. Each one looks like a black box, about the size of a pizza box, stacked in tall racks. Each rack might hold dozens of servers. Each server might hold terabytes of data. Multiply that by thousands of servers. The storage capacity is enormous. But here's something interesting. These servers aren't all the same. Some are for storage, some are for processing, some are for networking. They work together, like parts of a machine, all connected, all working toward the same goal: storing and serving data. The storage servers are the most important for our story. These are the ones that hold your photos, your videos, your messages. They're like digital filing cabinets. But instead of paper, they store ones and zeros, binary code, the language of computers. Each storage server might have multiple hard drives or solid-state drives. Each drive might hold several terabytes. Multiply that by the number of drives, by the number of servers, by the number of data centers. The total storage capacity is mind-boggling. But it's not infinite, it's finite, limited. There are boundaries, real boundaries, and we're approaching them faster than you might think. But here's something interesting. Your data might not be in just one place. It's probably copied, stored in multiple data centers, in different locations. Why? For safety. If one data center has a problem, your data is still safe somewhere else. It's like making backup copies of your homework. But on a massive scale, there are thousands of data centers around the world. Some are huge, covering acres of land. Some are smaller, hidden in cities. But they're everywhere, in every country, on every continent, all connected, all storing data. Now here's something you might not know. When you save something to the cloud, it's not actually in the sky. The cloud is just a name, a metaphor. Your data is actually stored in these data centers, physical buildings, real places, with real addresses. Companies like Google, Amazon, and Microsoft own massive data centers. They build them in specific places for specific reasons, near sources of cheap electricity, in cool climates to save on cooling costs, near major internet connections. They're strategic, carefully planned. Google has data centers all over the world. In the United States, in Europe, in Asia, in South America. Each one is strategically placed. Each one serves a region. Each one stores data for millions of people. Amazon's data centers power AWS, Amazon Web Services, one of the largest cloud computing platforms in the world. Millions of websites run on AWS. Millions of apps use AWS. All that data flows through Amazon's data centers. All that data needs storage. Microsoft's data centers power Azure, another massive cloud platform. Office 365 runs on Azure, so does Xbox Live, so do countless other services, all requiring storage, all needing space. These companies are constantly building new data centers, expanding capacity, adding storage, but can they build fast enough? Can they keep up with data creation? That's the question, that's the challenge. But data centers are just one part of the story. Your data doesn't just sit in one place, it travels, it moves. It flows through cables, under the ocean, across continents. Let me tell you about undersea cables. These are massive cables, lying on the ocean floor, connecting continents, carrying data across the world. They're like highways, but underwater, and instead of cars they carry data. Imagine laying one of these cables. It's an enormous project. Ships carry miles and miles of cable. They lay it carefully on the ocean floor. Sometimes it's buried, sometimes it just sits on the seabed. But it connects places, Europe to North America, Asia to Australia, all connected by cables under the sea. These cables are thick, protected by layers of insulation, designed to last decades. But they can break. Ships' anchors can damage them. Earthquakes can snap them. When they break, data stops flowing. Internet connections fail. Until repair ships can fix them. Let me tell you a story about a cable break. In 2008, several undersea cables broke near Egypt. They were damaged by ships' anchors. The result? Internet service across the Middle East and parts of Asia was disrupted. Millions of people lost internet access for days. The cables had to be repaired. Special ships had to be sent. The cables had to be pulled up from the ocean floor, fixed, then laid back down. It took weeks. During that time, internet service was limited, slow, unreliable. This shows how fragile the internet infrastructure can be, how dependent we are on these cables, how important they are, and how vulnerable they are to damage. But cables aren't just vulnerable to accidents, they're also limited in capacity. Each cable can only carry so much data, so much bandwidth. As data creation grows, cables can become bottlenecks. Limits on how fast data can travel. Limits on how much data can flow. Companies are constantly laying new cables, building more capacity. But it's expensive, it takes time, and there are only so many routes. Only so many places cables can go. There are hundreds of these undersea cables, a vast network, a web of connections, spanning the globe, carrying the data that makes the internet work. Without them, the internet as we know it wouldn't exist. But cables aren't the only way data travels. There are also satellites, beaming data through space, radio waves, wireless connections, all carrying data, all part of the infrastructure. Now let's talk about how your data actually gets stored. Inside those servers are storage devices, hard drives, solid-state drives. These are like digital filing cabinets, but instead of paper, they store ones and zeros. Binary code, the language of computers. A hard drive is a spinning disk, like a record player. But instead of music, it stores data. Tiny magnetic particles, arranged in patterns. Those patterns represent your photos, your videos, your messages, all stored as magnetic patterns on spinning disks. The disk spins incredibly fast, thousands of revolutions per minute. A tiny head reads and writes data, moving back and forth, finding the right spot, reading or writing information. It's precise, it's fast, but it's mechanical. Parts can wear out, disks can fail. Solid-state drives are different. No moving parts, just chips. Like flash drives but bigger, faster, more reliable. They're becoming more common, replacing hard drives in many places. SSDs work by storing electrical charges, tiny charges in tiny cells. Each cell can hold a bit of data, a 1 or a 0. Billions of cells, billions of bits, all storing data, all without moving parts. SSDs are faster than hard drives, much faster. They can read and write data almost instantly. No waiting for disks to spin, no waiting for heads to move, just pure speed. But SSDs have limits too. Each cell can only be written to so many times. After that, it wears out. Can't store data anymore. The drive fails. It's called write endurance. And it's a real limit. Both technologies have limits. Both have boundaries. Both can only store so much. Both can only last so long. And we're pushing those limits every day. With every byte we create. Hard drives can fail. Mechanical parts wear out. Disks can crash. Data can be lost. It happens more often than you might think. That's why redundancy is important. Why backups matter. Why multiple copies are stored. SSDs can also fail. Cells wear out. Write endurance limits are reached. Data becomes corrupted. Drives stop working. It's a reality, a risk, a challenge. Both technologies are improving, getting better, more reliable, more durable. But they still have limits, still have boundaries, still can fail, still need replacement. The challenge is managing these failures, planning for them, preparing for them. Building systems that can handle them, that can recover from them, that can continue working despite them. Data centers use redundancy for this reason. Multiple copies. multiple locations, multiple backups. If one drive fails, others take over. If one server fails, others continue. If one data center has problems, others keep working. It's resilience, it's reliability, it's necessary. But redundancy costs money, takes space, uses energy. It's a trade-off between reliability and cost, between safety and efficiency, between redundancy and capacity. Companies have to balance these, make choices, find the right balance. But here's the thing. Storage technology keeps improving. Getting smaller, getting bigger capacity, getting faster. What used to fill a room now fits in your pocket. But we still need those rooms, because we're creating more data than ever. Let me explain something called data redundancy. Remember how I said your data might be stored in multiple places? That's redundancy, making copies, storing the same data in different locations. Why? For safety, for speed. If your data is stored closer to you, it loads faster. That's why companies build data centers in many places. Your data might be copied to a data center near you. So when you want to see a photo, it doesn't have to travel across the world. It's nearby, fast. This is called a content delivery network. ACDN. It's like having libraries in every neighborhood. Instead of one big library far away, your books are nearby. Easy to access. Fast to retrieve. But all of this takes space. Physical space. Real estate. Data centers need land. They need buildings. They need power. Lots of power. And they need cooling. Lots of cooling. Here's a number that might surprise you. Some estimates suggest that data centers use about 1% of all the electricity in the world. 1% of all electricity. Everywhere. That's a lot of power. And that number is growing. Think about what that means. All those servers, running constantly, generating heat, using electricity, all to store our data, our photos, our videos, our messages. It takes real resources, real energy, real infrastructure. So when you save a photo to the cloud, remember this. That photo doesn't float in the sky, it lives in a building. A real building. With real servers, using real electricity. Connected by real cables, under real oceans. Let me tell you more about these data centers. Some are absolutely massive. The largest data centers cover millions of square feet. That's like multiple football fields. All filled with servers, all storing data, all connected to the internet. One of the largest data centers in the world is in Langfang, China. It covers over 6 million square feet. That's enormous. Imagine 100 football fields, all filled with computers, all storing data, all humming constantly. But size isn't everything. Efficiency matters too. Modern data centers are designed to be efficient, to use less energy, to store more data, to work better. But even the most efficient data center has limits. Physical limits, energy limits, space limits. Let me tell you about a specific data center. Imagine one owned by a major tech company. It might have 100,000 servers. Each server might store 10 terabytes. That's 1 petabyte per server. Multiply that by 100,000. That's 100 exabytes. In one data center, that's a lot of storage. But here's the thing. Even that massive amount of storage fills up. And when it does, the company has choices. Build more data centers, delete old data, or both. But building costs money. Deleting loses data. Neither is ideal. The internet is physical, it's infrastructure. It's buildings and cables and machines, all working together, all storing our data, all keeping our digital world running. But how much can it store? What are the limits? That's what we'll explore next. Because storage, as we'll discover, has boundaries. Real boundaries. And we're racing toward them. Chapter 3: How much can we actually store? The limits of storage. Storage has limits, real limits. Physical limits. You can't store infinite data. No matter how big your hard drive, no matter how many servers you have, there's always a limit, always a boundary. Let's start with a simple question. How much storage capacity exists in the world right now? The answer is huge, but it's also finite. Scientists estimate that humans have created about 100 zettabytes of storage capacity. That's 100 followed by 21 zeros. An almost unimaginable number. But here's the thing. We're not just storing new data, we're also keeping old data, data from years ago, decades ago, all of it stored somewhere, taking up space. And we're creating new data faster than storage capacity is growing. Think about all the old data, photos from years ago, videos from decades ago, messages from the past. All still stored, all still taking up space. We don't delete everything, we keep a lot, for history, for memories, for reference. But old data accumulates. Year after year. Decade after decade. It all adds up. All takes space. All needs storage. And we keep creating new data. Faster and faster, the total keeps growing. The storage needs keep increasing. Some companies archive old data, move it to cheaper storage, slower storage. But it's still stored, still taking up space, still costing money. Archive storage is cheaper. But it's not free. And it still has limits. The challenge is balancing old and new. What to keep, what to delete, what to archive, what to preserve. These are hard choices, important choices, choices that affect what we remember, what we preserve, what we lose. Let me tell you a story about storage growth. Back in the 1980s, a computer might have had a few megabytes of storage. That's enough for maybe one photo today. One single photo. Think about that. An entire computer, enough storage for one photo. I remember my first computer, it had 20 megabytes of storage. That seemed huge at the time. Enough for thousands of text documents, hundreds of simple programs. It felt like unlimited space. But today, 20 megabytes is nothing. A single high-resolution photo might be 10 megabytes. A short video might be 100 megabytes. A full-length movie might be several gigabytes. What seemed unlimited then seems tiny now. The growth has been incredible, exponential. Every few years storage capacity doubles, gets bigger, gets cheaper, gets better. But data creation grows even faster, much faster. Back in the 1980s, people created maybe a few megabytes of data per person per year. Today, people create gigabytes, maybe terabytes, per person, per year. The growth is staggering, the acceleration is incredible. By the 1990s, computers had gigabytes, enough for hundreds of photos, thousands of documents. By the 2000s, terabytes became common. Enough for millions of photos, entire libraries of information. Today, we're talking about petabytes and exabytes, massive amounts of storage. A petabyte is 1,000,000 gigabytes. An exabyte is 1,000,000,000 gigabytes. These are enormous numbers, almost impossible to comprehend. But here's the problem. Data creation is growing faster than storage capacity. Much faster. We're creating data at an exponential rate. Storage capacity grows too. But not as fast. Not fast enough. The gap is widening, the challenge is growing. Let me put this in perspective. In 2020, the world had about 6 zettabytes of storage capacity. But we created about 64 zettabytes of data that year. That's more than 10 times what we could store. We're creating data 10 times faster than we can store it. Now, not all data needs to be stored permanently. Some data is temporary, some gets deleted quickly, but a lot of it gets stored for a long time, maybe forever. And that's the challenge. That's the problem we need to solve. Let me give you some numbers. In 2020, humans created about 64 zettabytes of data. But we only had about 6 zettabytes of storage capacity. That's a huge gap. We're creating data 10 times faster than we can store it, or at least we were. The gap is concerning. It means we're not storing everything. We're deleting things, making choices, deciding what to keep, what to lose. And those choices are getting harder. The gap is getting bigger. There's something called Moore's law. It's not really a law, more like an observation. It says that computer power doubles about every 2 years. Storage capacity has followed a similar pattern, getting bigger, getting cheaper, getting better. For decades, Moore's law held true. Storage capacity doubled every couple of years. Prices halved. Everything got better, faster, cheaper. It seemed unstoppable. But Moore's law might be slowing down. We're reaching physical limits. You can only make things so small. You can only pack so much into so little space. The laws of physics create boundaries. Real boundaries. Hard boundaries. But Moore's law might be slowing down. We're reaching physical limits. You can only make computer chips so small. You can only pack so much data into so little space. There are fundamental limits. The laws of physics create boundaries. Let me explain the physical limits. Data storage works by storing information in tiny spaces. On hard drives, it's magnetic particles. On solid-state drives, it's electrical charges. But these particles and charges have a minimum size. You can't make them infinitely small. At some point you hit quantum limits. The particles become so small that quantum physics takes over. Strange things happen. Data becomes unstable, unreliable. You can't store information reliably anymore. Quantum mechanics is strange. At tiny scales, particles behave differently. They can be in multiple states at once. They can tunnel through barriers. They can be entangled with other particles. It's weird. It's unpredictable. It's not good for reliable storage. Scientists are working on solutions, new technologies, better methods. But there are always limits, always boundaries, always a point where you can't go further. Some scientists think we might be able to use quantum mechanics. Instead of fighting it, use it to our advantage. Quantum storage could be incredibly dense. But it's incredibly difficult. Still mostly theoretical, still years away, maybe decades. The point is this: physical limits are real. We can't ignore them. We can't wish them away. We have to work within them. Or find ways around them. But that's getting harder. The limits are getting closer. The boundaries are getting tighter. Now let's talk about energy. Storage doesn't just need space. It needs power, electricity, lots of it. And that creates another limit. Data centers use enormous amounts of energy. Some use as much electricity as a small city. Think about that. One data center, using as much power as an entire city. And there are thousands of data centers, all using power, constantly. The energy isn't just for storing data, it's for running servers, for cooling systems, for keeping everything working. All of that takes power, and power costs money, and power has limits. Let me break down where the energy goes. About 40% goes to running the servers, processing data, storing data, serving data. About 40% goes to cooling, keeping servers from overheating. The remaining 20% goes to other things. Networking, security, lighting, all of it uses energy. As data centers get bigger, energy use grows. As we store more data, energy needs increase. As we create more data, energy demands rise. It's a cycle, a challenge, a constraint. Some data centers are trying to be more efficient, using better servers, better cooling, better design, but even the most efficient data center uses enormous amounts of energy. There's no way around it. Storing data takes energy, lots of it. Renewable energy helps. Solar panels, wind turbines. But they have limits too. They're not always available. They need backup, they need storage. For the energy itself, it's complex, it's challenging. But it's necessary. What happens if we run out of energy? Or if energy becomes too expensive? Storage becomes impossible. Or at least, very difficult. Energy is a real constraint. A real limit. Let me give you a specific example. A large data center might use 100 megawatts of power. That's enough to power 100,000 homes. One data center. Using that much power. Constantly. Day and night. Never stopping. Now imagine thousands of data centers, all using similar amounts of power. The total energy consumption becomes enormous. It's like powering millions of homes. Just for data storage, just for the internet. And the energy use is growing. As we build more data centers, as we store more data, as we create more data, the energy needs keep growing, faster and faster. What if energy becomes scarce? What if we need to reduce energy use? For environmental reasons, for economic reasons. Data storage becomes harder, more expensive, more limited. Energy is a real constraint, a real limit. Let me tell you about cooling. All those servers generate heat. Lots of heat. If they get too hot, they break. So data centers need massive cooling systems, air conditioning on an enormous scale. The heat is incredible. Thousands of servers, all generating heat, all the time. The temperature can rise quickly. Without cooling, servers would overheat, fail, break, stop working. I've heard stories about data centers where the temperature can reach dangerous levels in minutes if cooling fails. The heat is that intense. The servers generate that much energy. It's like having thousands of space heaters running constantly, all in one building. So data centers have massive cooling systems. Air conditioning units, cooling towers, water systems, all working to keep servers cool, all using energy, all costing money. Some data centers use innovative cooling methods. Liquid cooling, where servers are submerged in special fluids, or using outside air when it's cold, or using water from nearby sources, all to reduce energy use, all to save costs, all to be more efficient. But cooling is still a major expense, still a major energy user, still a major constraint. It's part of the challenge, part of the limits, part of what we need to solve. Innovation in cooling is happening. New methods, better systems, more efficient approaches. But cooling will always be needed. As long as we have servers, as long as we store data. Cooling is essential, and it uses energy, lots of it. The challenge is reducing that energy use, making cooling more efficient, using renewable energy, finding better methods. It's an ongoing effort, an ongoing challenge, an ongoing race. Some data centers are already using renewable energy, solar panels on roofs, wind turbines nearby, hydroelectric power. It's happening, it's working. It's the future. But not all data centers use renewable energy, not yet. The transition takes time, takes investment, takes commitment, but it's happening, slowly. steadily, progressively. But it's a race we can win, with innovation, with efficiency, with renewable energy. The solutions exist, we just need to apply them, to use them, to make them work. The future of data storage is sustainable, or it needs to be. We can't keep using fossil fuels forever. We can't keep increasing energy use indefinitely. We need sustainable solutions. And we're working on them, we're building them, we're implementing them. Sustainability isn't optional, it's necessary, for the environment, for the future, for survival. Data storage must become sustainable, or we'll face consequences. Real consequences, environmental consequences, economic consequences, social consequences. But we're making progress. Renewable energy is growing, efficiency is improving. Innovation is happening. The transition is underway, slowly, steadily. But it's happening. The future is becoming sustainable, one data center at a time, one innovation at a time, one choice at a time. Some data centers use as much energy for cooling as they do for computing, half their power, just to stay cool. That's a lot of energy. A lot of resources, a real constraint. Companies are building data centers in cold places, near the Arctic, in cold climates, to save on cooling costs, to reduce energy use. But there are only so many cold places, only so many locations. Let me tell you a story about energy limits. Imagine a data center that needs 100 megawatts of power. That's enough to power 100,000 homes. One data center. Using that much power. Constantly. Day and night, never stopping. Now imagine thousands of data centers, all using similar amounts of power. The total energy consumption becomes enormous. It's like powering millions of homes, just for data storage, just for the internet. What happens if energy becomes scarce? Or expensive? Or if we need to reduce energy use for environmental reasons? Data storage becomes harder, more expensive, more limited. Energy is a real constraint, a real limit. But energy isn't the only limit. There's also cost. Building data centers costs billions of dollars. Running them costs millions every year. Maintaining them costs even more. All of that adds up. A single large data center might cost $1 billion to build. Then millions every year to run. That's a lot of money. And companies have to make that money back, through services, through subscriptions, through advertising. But here's the challenge. Storage is getting cheaper, but we're creating more data, so even though storage costs less per unit, we need more units. The total cost keeps growing, even as prices fall. Let me explain the economics. Imagine storage costs $1 per terabyte. That seems cheap. But if you need 1,000,000 terabytes, that's $1 million. And if you need 1 billion terabytes, that's $1 billion. The numbers add up fast. Companies have to balance costs and capacity. They can't just build unlimited storage. They have to make choices. Strategic choices. Economic choices. Choices that affect what gets stored, what gets deleted, what gets preserved. Now let's talk about cost. Storage costs money. Building data centers costs money. Running them costs money. Maintaining them costs money. All of that adds up. A large data center might cost $1 billion to build. Then tens of millions every year to run. That's a lot of money, and companies need to make that money back. Through services, through subscriptions, through advertising. But here's the challenge. Storage costs are falling, but data creation is rising faster. So even though storage gets cheaper, we need more of it. The total cost keeps growing, even as prices fall. Companies have to balance costs and capacity. They can't just build unlimited storage. They have to make choices. Strategic choices, economic choices, choices that affect what gets stored, what gets deleted, what gets preserved. The economics of storage are complex. It's not just about building more, it's about building smarter, more efficiently, more strategically. That's the challenge. That's what companies are working on. Some companies are investing heavily in storage, building massive data centers, expanding capacity. Others are focusing on efficiency, making better use of existing storage. Both approaches matter, both are needed. The key is finding the right balance between capacity and cost, between growth and efficiency, between building more and using better. It's a complex equation with many variables, many factors, many choices. But the trend is clear. Storage needs are growing faster than capacity, faster than efficiency improvements. The gap is widening, the challenge is growing, the race is intensifying. The good news is that storage is getting cheaper. What cost thousands of dollars decades ago now costs pennies. But it still costs something. And when you're storing zettabytes of data, even pennies add up to billions of dollars. Companies have to make choices. What data to keep, what data to delete. What's worth storing, what's not. It's a constant calculation, a constant decision. But here's something interesting. Even if storage were free, there would still be limits, physical space limits. You can only build so many data centers. You can only fit so many servers in a building. You can only build so many buildings. Land is limited. Space is limited. Even in the digital world, physical reality creates boundaries. You can't store infinite data because you can't build infinite buildings. Let me explain the difference between storage and bandwidth. These are two different things. Two different limits. Storage is how much data you can keep, like how many books fit in a library. Bandwidth is how fast you can move data, like how many books you can check out at once. You might have enough storage, but if your bandwidth is too slow, you can't access your data quickly, or you might have fast bandwidth. But if your storage is full, you can't save new data. Both create limits. Both create constraints, both can cause problems. Now here's a question. Why can't we just keep building more data centers, more servers, more storage, forever? The answer is that we can. For a while, but there are practical limits. Economic limits, environmental limits, social limits. Building data centers takes resources, materials, energy, land. All of that is finite. All of that has limits. And building more creates more problems, more energy use, more environmental impact, more cost. At some point it becomes unsustainable. At some point we hit real boundaries, not just technical boundaries, but practical ones, real-world ones. Scientists are working on new storage technologies. DNA storage. Storing data in DNA molecules, the same molecules that carry genetic information. It's incredibly dense. A single gram of DNA could theoretically store all the data in the world. But it's still experimental, still being developed, still years away from practical use. And even DNA storage would have limits. Physical limits. Practical limits. Quantum storage is another possibility, using quantum physics to store data. Incredibly dense. Incredibly fast. But also incredibly difficult. Still mostly theoretical. Still being researched. Holographic storage uses light, storing data in 3 dimensions. Instead of on a surface, potentially much more dense, but also still experimental. The point is this: we're working on solutions, but solutions take time. And in the meantime, we're creating data faster than ever. The race is on. Can we build storage fast enough? Can we keep up? The answer, as we'll discover, is complicated. Because storage has limits. Real limits, and we're approaching them faster than we might realize. What happens when we reach those limits? That's what we'll explore next. Because the consequences are real, and they're coming sooner than you might think. Chapter 4: The Breaking Point. What happens when storage fills up? What happens when storage fills up? It's not like a light switch. The internet doesn't just turn off. It's more gradual, more complex, more concerning. Let's start with something you've probably experienced. Your computer's hard drive getting full. What happens? It starts slowing down. Programs take longer to load. Everything becomes sluggish, frustrating. I remember when my computer's hard drive got full. It was frustrating. Everything took forever. Opening a program, wait. Saving a file, wait. Even moving the mouse felt slow. The computer was struggling, working harder, but doing less. The reason is simple. When storage is full, the computer has to work harder to find space. It has to search. It has to reorganize. It has to make room. All of that takes time, takes processing power, makes everything slower. Now imagine that happening to the entire internet, not just your computer, but every server, every data center, every storage system. All getting full, all slowing down, all struggling. That's what could happen. That's the breaking point. But it's not just about speed, it's also about reliability. When storage is full, systems become unstable, more likely to crash, more likely to fail, more likely to lose data. The risk increases, the problems multiply. Now imagine that happening to the entire internet, not just your computer, but every server, every data center, every storage system, all getting full, all slowing down. That's what could happen. That's the breaking point. Let me tell you a story about what happens when storage gets full. Imagine a data center. It's running normally. Servers humming, data flowing, everything working smoothly. Then storage starts filling up. Not all at once, gradually, day by day, week by week. At first nothing changes, there's still space, still room for more data. But then it gets tighter, servers have less free space, they start working harder, processing slows down, response times increase. Then it gets worse. Storage becomes critical, servers can't find free space easily, they have to search harder, work harder. Everything slows down. Websites take longer to load. Videos buffer more. Messages take longer to send. Imagine trying to find something in a closet that's completely full. You have to move things around, search through everything. It takes time. It's frustrating. That's what happens to servers when storage is full. They have to work harder, search longer. Everything slows down. The slowdown isn't uniform. Some things slow down more than others. Popular content might still load quickly. It's cached, stored in fast storage. But less popular content, it slows down dramatically, takes forever to load, maybe doesn't load at all. Users notice, they get frustrated, they complain. They might stop using services, which creates its own problems. But the underlying issue remains. Storage is full, systems are struggling, everything is degrading. Finally, storage fills up completely. No more space. Zero. What happens then? The system has to make choices, hard choices. What data to keep? What data to delete? Who decides? It's like a library that's completely full. No more shelves, no more space. But new books keep arriving. What do? You have to remove old books. Make room for new ones. But which books? Which ones are important? Which ones can go? That's the dilemma, that's the challenge. When storage is full, something has to go. But what? Who decides? How do you choose? Some systems use algorithms, automated decisions. Delete the oldest data, delete the least accessed data, delete data that hasn't been used in a while. But algorithms aren't perfect. They make mistakes. They delete important things. They keep unimportant things. Other systems use human decisions. People review data, decide what to keep, what to delete. But that's slow, expensive, doesn't scale, can't handle billions of pieces of data. The challenge is finding the right balance between automation and human judgment, between efficiency and preservation, between cost and value. It's not easy, it's not simple, but it's necessary. This is called the data deletion dilemma. When storage is full, something has to go. Old data gets deleted, unused data gets removed. But who decides what's old, what's unused, what's important? Let me explain what might get deleted first. Usually it's the least accessed data, data that hasn't been used in a long time, old backups, archived files, things people haven't looked at in years. But here's the problem: old data might be important, historical records, family photos, research data. Just because it's old doesn't mean it's worthless. But when storage is full, choices have to be made. Think about historical photos, old family pictures, documents from decades ago. They might not be accessed often, but they're valuable, important, part of history, part of memory. Should they be deleted just because they're old, just because they're not accessed? Think about research data, scientific studies from years ago. They might not be current, but they're valuable, important for understanding, for reference, for building on past work. Should they be deleted just because they're old? The challenge is determining value. What's important? What's worth keeping? What can be deleted? These aren't easy questions. They don't have simple answers. But they need to be answered. When storage is full, choices must be made. Companies might delete data based on value. What makes money stays, what doesn't gets deleted. Popular content stays, unpopular content goes. It's a business decision, driven by economics, by profit, by cost. Or they might delete based on access. What people use stays, what they don't gets removed. Frequently accessed data stays, rarely accessed data goes. It's an efficiency decision, driven by usage, by patterns, by statistics. But these decisions aren't perfect. Valuable content might get deleted, important data might be lost, historical records might disappear. Just because they're not popular, just because they're not accessed, just because they don't make money. The challenge is balancing value and cost. What's worth keeping? What's worth the storage cost? What can be deleted? These are complex questions, with complex answers, answers that affect what we preserve, what we lose, what we remember. But this creates problems. What if important data gets deleted? What if we lose something valuable? What if we can't get it back? Now let's imagine this happening globally. Not just one data center, but many. All filling up, all making hard choices, all deleting data. The internet starts degrading. Not breaking, but degrading. Getting worse. Getting slower. Websites load slower. Videos buffer constantly. Messages take forever to send. Downloads crawl. Everything becomes frustrating. Everything becomes difficult. But it gets worse. Some services might shut down completely. If they can't store data, they can't operate, they have to close, stop working, go offline. Imagine if social media platforms started shutting down, or video streaming services, or cloud storage. What would happen? How would people communicate? How would they access information? Let me explain the cascade effect. It's like dominoes falling. One problem causes another, which causes another, which causes another. Storage fills up, services slow down, people try to use services more, creating more data, making the problem worse. Services shut down, people panic, create even more data trying to save things. The problem accelerates, gets worse, faster. Critical services might be protected, hospitals, banks, emergency services. They might get priority, but everything else, It's vulnerable, at risk, could fail. What happens to essential services? Hospitals store patient records digitally. Banks store financial data. Power grids use digital systems. What if their storage fills up? What if they can't store critical data? The consequences could be serious. Very serious. Not just inconvenient, but dangerous. Life-threatening even. Let me explain the difference between bandwidth and storage. These are two different limits, but they're related. Bandwidth is how fast data can move. Like the width of a highway, more lanes mean more traffic can flow. But if the highway is full of stopped cars, more lanes don't help. Storage is how much data can be kept, like parking spaces. If all the parking is full, new cars can't park, even if the highway has lots of lanes. When storage fills up, bandwidth becomes less useful. You can move data fast. But if there's nowhere to store it, what's the point? The system breaks down. Now let's talk about what paralyzing the internet would actually look like. It wouldn't be instant, it would be gradual, a slow decline, a gradual breakdown. First, things get slower, websites take longer to load, videos buffer, messages delay. Annoying but manageable. Then things get worse, some services fail, websites go offline, apps stop working, frustrating and concerning. Then critical services start failing, banks can't process transactions, hospitals can't access records, power grids have problems, dangerous and scary. Finally, widespread failure, large portions of the internet go offline, communication breaks down, information becomes inaccessible, society starts breaking down. Imagine a world without the internet. No social media, no video streaming, no online shopping, no email, no cloud storage. Life would change dramatically. The way we work, the way we communicate, the way we live. Some things would still work. Local networks, offline systems, but the global internet, the interconnected web, it would be broken, fragmented, incomplete. How long would recovery take? That depends. If it's just storage filling up, recovery might be possible. Build more storage. Delete old data. Restore services. But it would take time. Weeks, maybe months. But building new storage takes time. Data centers don't appear overnight. They take months to build, years to plan, and they cost billions of dollars. Recovery wouldn't be quick, or easy, or cheap. If critical data is lost, if systems are damaged, recovery could take much longer, years even. Some things might never be recovered, lost forever, gone. The economic impact would be enormous. Businesses depend on the internet. If it fails, businesses fail, jobs are lost, economies collapse. The cost would be in the trillions, maybe more. Think about all the businesses that rely on the internet, online stores, streaming services, social media platforms, cloud computing companies. If the internet fails, they all fail. Millions of jobs, billions of dollars, all lost. But if critical data is lost, if systems are damaged, recovery could take much longer, years even. Some things might never be recovered. The economic impact would be enormous. Businesses depend on the internet. If it fails, businesses fail, jobs are lost, economies collapse. The cost would be in the trillions, maybe more. The social impact would be profound. People depend on the internet for communication, for information, for connection. If it fails, society changes, maybe permanently. Think about how you communicate. Probably mostly online. Text messages, social media, video calls. If the internet fails, all of that stops. How would you stay in touch? How would you connect? Think about information, news, research, education. So much of it is online. If the internet fails, information becomes scarce, hard to access, hard to share. Knowledge becomes fragmented, isolated. But here's something important. This is a worst-case scenario. It's not inevitable. It's not guaranteed. We can prevent it. We can prepare for it. We can solve it. The key is understanding the problem, recognizing the limits, working on solutions, before it's too late. Before we reach the breaking point, before systems fail, before society is impacted. We have time, not unlimited time, but time. Time to innovate, time to build, time to solve. The question is, will we use it? Will we act? Will we solve the problem before it becomes a crisis? Let me tell you a more detailed story about what happens when storage fills up. Imagine a popular video streaming service. Millions of people use it. Billions of hours of content, all stored on servers, all taking up space. As storage fills up, the service has choices. It can build more storage, but that costs money. Takes time, or it can delete old content that fewer people watch, but that loses data, loses history. What if they delete something important? Something historical, something valuable. It's gone forever, can't get it back. That's the dilemma, the impossible choice. Now imagine this happening across the internet. Not just one service, but many, all facing the same problem, all making hard choices, all deleting data, all losing information. The internet starts shrinking. Not physically, but in terms of what's available, what's accessible, what's preserved. Information disappears, content vanishes. History is lost. But it's not just about losing old content. It's also about not being able to create new content. If storage is full, you can't save new things. You can't upload new videos. You can't post new photos. Creation stops. Innovation stops. Growth stops. Let me explain what happens to different types of services. Social media platforms might start deleting old posts after a certain time, or if they're not popular. Email services might delete old emails. Cloud storage might delete unused files. But here's the problem. What's old to one person might be valuable to another. What's unused might be important. What's unpopular might be historical. The choices are difficult. The consequences are real. The key is understanding the problem, recognizing the limits, working on solutions, before it's too late, before we reach the breaking point. So remember this, storage has limits. When those limits are reached, systems degrade, services fail, society is impacted, the consequences are real. But so are the solutions, and that's what we'll explore next. Because humans are problem solvers, and this is a problem we can solve. Chapter 5, The Race Against Time. Can we keep up? Humans are problem solvers. We face challenges. We find solutions. We innovate. We adapt. The data storage challenge is huge. But so is human ingenuity. Scientists and engineers are working on solutions. Racing against time. Racing against the data explosion. Let's start with innovation. New storage technologies are being developed. Amazing technologies. Technologies that might solve our problems, or at least help us keep up. DNA storage is one possibility. It sounds like science fiction, but it's real. Scientists have successfully stored data in DNA molecules, the same molecules that carry genetic information in living things. Here's how it works. Data gets converted into DNA code, the same code that makes up genes. Then that DNA is synthesized, created in a lab, stored. When you want the data back, you sequence the DNA, read the code, convert it back to data. The advantages are incredible. DNA is incredibly dense. A single gram could theoretically store all the data in the world, all of it, in 1 gram. Think about that. DNA is also stable. It can last for thousands of years, maybe longer, under the right conditions. It doesn't need electricity, it doesn't need cooling, it just sits there, storing data, forever. But there are challenges. DNA storage is slow. Reading and writing takes time.
Hours, maybe days.
It's also expensive. Very expensive. For now at least. Scientists are working on making it faster, cheaper, more practical. It might be decades before it's widely used. But it's coming. The technology is real. The potential is enormous. Quantum storage is another possibility. Using quantum physics to store data, quantum mechanics allows for incredible density. Information stored at the quantum level, the smallest possible scale. But quantum storage is incredibly difficult. Quantum states are fragile, they're easily disturbed. A single photon can destroy quantum information. It's like trying to balance a pencil on its tip. Possible, but very difficult. Quantum mechanics is strange. At tiny scales, particles behave differently. They can be in multiple states at once. They can tunnel through barriers. They can be entangled with other particles. It's weird. It's unpredictable. It's not good for reliable storage. But quantum storage could be incredibly dense. Information stored at the quantum level. The smallest possible scale. Potentially storing massive amounts of data in tiny spaces. The potential is enormous. But so are the challenges. Scientists are working on quantum storage, making progress, but it's still mostly experimental. Still years away, maybe decades. The technology is complex. The challenges are significant. But the potential is there. The possibility exists. Quantum storage might be the future. Or it might not. Only time will tell. Only research will reveal. But scientists are exploring, innovating, pushing boundaries. That's how progress happens. That's how solutions are found. Scientists are working on it, making progress. But it's still mostly experimental, still years away, maybe decades. But the potential is there, the possibility exists. Holographic storage uses light, storing data in 3 dimensions, instead of on a surface, like a hard drive. Data is stored throughout a volume, like a cube of information. This could be much more dense than current storage, potentially thousands of times more dense, but it's also still experimental. Still being developed, still facing challenges. Holographic storage works by storing data in 3 dimensions, instead of on a surface, like a hard drive. Data is stored throughout a volume, like a cube of information. This allows for much more density, much more capacity. Scientists have demonstrated holographic storage. Stored data in crystals, retrieved it successfully. It works, it's real. But it's still experimental, still being developed, still facing challenges. The challenges include cost. Holographic storage is expensive, very expensive. For now, it's also complex, requires specialized equipment, specialized materials. But scientists are working on solutions, making it cheaper, more practical, more accessible. Holographic storage might be part of the solution, or it might not. But it's being explored, it's being developed, it's part of the race, part of the effort to solve the storage challenge. But innovation isn't just about new technologies. It's also about improving what we have, making existing storage better, more efficient, more capable. Data compression is one way, making files smaller, without losing information, or with minimal loss. It's like folding clothes to fit more in a suitcase. Same clothes, less space. Compression algorithms keep improving, getting better, more efficient. Scientists are developing new methods, better methods. Methods that can compress data more, save more space. Let me explain how compression works. Imagine you have a file with the word hello, repeated 1,000 times. Instead of storing hello 1,000 times, compression stores it once, plus a note that says repeat this 1,000 times. That saves space. A lot of space. Real compression is more complex, but the idea is the same. Find patterns, find repetition, find ways to represent data more efficiently, use less space, store more information. Modern compression can reduce file sizes dramatically. A video file might be 1 gigabyte uncompressed, but compressed it might be only 100 megabytes. That's 10 times smaller, 10 times less storage needed. But compression has limits. You can only compress so much. At some point, you lose information, quality degrades, the file becomes unusable. There's a balance, a trade-off between size and quality. Scientists are constantly working on better compression, new algorithms, better methods, ways to compress more without losing quality. It's an ongoing challenge, an ongoing race. Deduplication is another technique. Finding duplicate data, removing copies, keeping only one. If 1 million people have the same photo, you don't need to store it 1 million times. Store it once, point everyone to that one copy. This saves enormous amounts of space, especially for popular content, videos that millions of people watch, photos that thousands of people share. Deduplication can save massive amounts of storage. Let me give you an example. Imagine a viral video. Millions of people save it, share it, send it to friends. Without deduplication, that video gets stored millions of times, millions of copies, all taking up space. With deduplication, the video gets stored once, just once. Everyone who wants it gets a pointer, a link, to that one copy. The storage savings are enormous. Instead of millions of copies, just one. That's deduplication. That's efficiency. Companies use deduplication extensively. It's one of the most effective ways to save storage, to reduce costs, to maximize capacity. But even deduplication has limits. Not everything is duplicated. Not everything can be deduplicated. Unique content still needs storage. Personal photos, personal videos, personal messages. These can't be deduplicated. They're unique. They need their own storage. And there's a lot of unique content. Billions of pieces, all needing storage. Think about your own personal data, your photos, your videos, your messages. They're unique to you. They can't be deduplicated. They need their own storage. And you're not alone. Billions of people, each with unique data, each needing storage. The challenge is that unique data is growing faster than duplicated data. As people create more personal content, more unique photos, more unique videos, more unique messages, the storage needs grow. The challenge increases. Deduplication helps. But it's not enough. Not by itself. We need other solutions, other techniques, other innovations. The storage challenge requires multiple solutions, multiple approaches, multiple innovations working together. Better algorithms help too. Smarter software, more efficient code, using storage more intelligently, organizing data better, accessing it more efficiently. But technology alone might not be enough. We might also need to change how we create data, how we use data, how we think about data. Let me tell you about digital minimalism. It's a movement, a philosophy, the idea that we don't need to save everything. We can be selective. We can choose what's important, what's worth keeping. Not every photo needs to be saved forever. Not every message needs to be archived. Not every video needs to be stored. We can be more selective, more thoughtful, more intentional. This doesn't mean deleting everything, it means being mindful. thinking about what we create, what we save, what we really need. Companies are also getting smarter, using data more efficiently, storing only what's necessary, deleting what's not, making better choices, being more strategic. But here's the challenge. The race is constant. Data creation keeps accelerating. Storage capacity needs to keep up, or exceed, or we need to slow data creation, or both. The gap between data creation and storage capacity is the key. If we create data faster than we can store it, we have a problem. If we can store data faster than we create it, we're okay, for now. But the trend is concerning. Data creation is accelerating, storage capacity is growing, but maybe not fast enough. The gap might be closing, or even reversing. Scientists are working on solutions. Multiple solutions, different approaches, some technological, some behavioral, some both. The goal is to stay ahead, to keep up, to solve the problem. But it's a race. A constant race. And the finish line keeps moving. As we solve problems, new ones appear. As we build capacity, we create more data. It's a cycle, a challenge, but one we can meet. The key is awareness, understanding the problem, working on solutions, not panicking, but not ignoring it either, taking it seriously, working on it, solving it. Let me tell you more about DNA storage. Scientists have already stored data in DNA. Real data, real files. They've stored books, photos, even videos. All encoded in DNA molecules. The process is fascinating. First, data gets converted to binary code, ones and zeros. Then that binary code gets converted to DNA code. The 4 letters of DNA, A, T, C, G. Then that DNA gets synthesized, created molecule by molecule. When you want the data back, you sequence the DNA, read the code. Convert it back to binary, then back to the original data. It works. It's real. It's happening. But there are challenges. DNA storage is slow. Reading and writing takes hours, sometimes days. It's also expensive, very expensive. For now. But scientists are working on it, making it faster, making it cheaper. The potential is enormous. DNA is incredibly stable. It can last for thousands of years, under the right conditions. It doesn't need electricity, it doesn't need cooling, it just sits there, storing data, forever. Scientists have successfully stored data in DNA, real files. They've stored books, photos, videos, even entire operating systems, all encoded in DNA, all stored in molecules, all preserved. The density is incredible. A single gram of DNA could theoretically store 215 petabytes of data. That's 215 million gigabytes in 1 gram. Think about that. All the data in the world, stored in a space smaller than a sugar cube. But DNA storage has challenges. It's slow. Reading and writing takes hours, sometimes days. It's expensive, very expensive. For now, it's also complex, requires specialized equipment, specialized knowledge. Scientists are working on solutions. Making DNA storage faster, cheaper, more practical. It might be decades before it's widely used, but the potential is there. The possibility exists. The future might be written in DNA. Imagine storing all human knowledge in DNA, all books, all photos, all videos, everything, in a space smaller than a sugar cube. That's the potential, that's the future, maybe. Quantum storage is another possibility, using quantum physics, the strange rules that govern tiny particles. Quantum mechanics allows for incredible density, information stored at the quantum level, the smallest possible scale. But quantum storage is incredibly difficult. Quantum states are fragile. They're easily disturbed. A single photon can destroy quantum information. It's like trying to balance a pencil on its tip. possible, but very difficult. Scientists are working on it, making progress, but it's still mostly experimental, still years away, maybe decades. But the potential is there. The possibility exists. Holographic storage uses light, storing data in 3 dimensions. Instead of on a surface, like a hard drive, data is stored throughout a volume, like a cube of information. This could be much more dense than current storage, potentially thousands of times more dense. But innovation isn't just about new technologies, it's also about improving what we have, making existing storage better, more efficient, more capable. Data compression keeps improving. New algorithms, better methods, more efficient techniques. Scientists are constantly working on better compression. Ways to make files smaller, without losing quality, or with minimal loss. Deduplication saves enormous space, finding duplicate data, removing copies, keeping only one. If 1 million people have the same photo, you don't need to store it 1 million times. Store it once. Point everyone to that one copy. This saves massive amounts of storage. Better algorithms help too. Smarter software, more efficient code, using storage more intelligently, organizing data better, accessing it more efficiently. All of this helps. All of this matters. Algorithms are like recipes, instructions for computers. Better algorithms mean better results, more efficient storage, faster access, less waste, more capacity. Think about how algorithms work. They're sets of instructions, step by step, telling computers what to do, how to organize data, how to access it, how to manage it. Better instructions mean better results. Scientists are constantly developing better algorithms, smarter ways to organize data, more efficient ways to access it, better ways to manage it. It's an ongoing effort, an ongoing improvement, an ongoing race. Machine learning is helping too. Algorithms that learn, that improve, that adapt. They can optimize storage, predict usage, manage resources. It's powerful, it's promising, it's part of the solution. But algorithms alone aren't enough. They need hardware to run on. They need infrastructure to support them. They need systems to implement them. It's all connected. All part of the solution. All part of the challenge. The solution requires everything working together. Hardware and software, algorithms and infrastructure. Technology and innovation, all connected, all working toward the same goal, solving the storage challenge. But technology alone might not be enough. We might also need to change how we create data, how we use data, how we think about data. Digital minimalism is a movement, a philosophy. The idea that we don't need to save everything, we can be selective, we can choose what's important, what's worth keeping. Not every photo needs to be saved forever. Not every message needs to be archived. Not every video needs to be stored. We can be more selective, more thoughtful, more intentional. This doesn't mean deleting everything. It means being mindful, thinking about what we create, what we save, what we really need. Companies are also getting smarter, using data more efficiently, storing only what's necessary, deleting what's not, making better choices, being more strategic. But here's the challenge. The race is constant. Data creation keeps accelerating. Storage capacity needs to keep up, or exceed, or we need to slow data creation, or both. The gap between data creation and storage capacity is the key. If we create data faster than we can store it, we have a problem. If we can store data faster than we create it, we're okay, for now. But the trend is concerning. Data creation is accelerating. Storage capacity is growing. But maybe not fast enough. The gap might be closing, or even reversing. Scientists are working on solutions, multiple solutions, different approaches, some technological, some behavioral, some both. The goal is to stay ahead, to keep up, to solve the problem. But it's a race, a constant race, and the finish line keeps moving. As we solve problems, new ones appear. As we build capacity, we create more data. It's a cycle, a challenge, but one we can meet. The key is awareness. Understanding the problem, working on solutions, not panicking. But not ignoring it either, taking it seriously, working on it, solving it. Because humans are problem solvers, we've faced challenges before, we've solved them, we'll solve this one too. It might take time, it might take effort, it might take innovation, but we'll do it, we always do. So remember this, the race is on, scientists are working, engineers are innovating, solutions are coming. But we need to keep running, keep working, keep solving. Because the data keeps coming, and we need to be ready. Chapter 6: The Bigger Picture: Data, Society and Our Digital Future. The data storage challenge isn't just about technology, it's about something bigger. Something deeper. It's about what data means, what information means, what we're really storing, and why it matters. Let's start with what data actually represents. It's not just ones and zeros, it's not just bits and bytes, it's human knowledge, human memories, human communication. It's photos of birthdays, videos of graduations, messages between friends. It's history, it's culture, it's us. When we talk about storing data, we're really talking about preserving memories, saving knowledge, keeping information. It's about what matters, what's important, what we want to remember. Let me tell you a story about preserving history. Imagine if we lost all digital records. All photos, all videos, all messages. What would we lose? Years of memories. Decades of history. Generations of knowledge. That's what's at stake. Not just storage, but preservation. Not just capacity, but memory. Not just technology, but humanity. Now let's talk about balance. The data storage challenge reflects a bigger question. How do we balance growth and limits? Innovation and sustainability, progress and responsibility. It's like riding a bike. Too slow and you fall over, too fast and you crash. You need balance, the right speed, the right pace, the right approach. We need innovation, we need progress, we need to keep moving forward. But we also need limits, we need sustainability, we need to be responsible. Finding that balance is the challenge. The data storage challenge connects to other challenges: climate change, resource use, environmental impact. They're all related, all connected, all part of the same bigger picture. Data centers use energy, lots of energy. That energy comes from somewhere, often from fossil fuels, creating carbon emissions, contributing to climate change. Building data centers uses resources, materials, land, water, all finite, all limited, all part of the environmental impact. So solving the data storage challenge isn't just about storage, it's about energy, about resources, about the environment, about sustainability, about the future. But here's something important. We can solve these challenges together. We can innovate sustainably. We can grow responsibly. We can progress thoughtfully. Renewable energy can power data centers, solar, wind, hydroelectric, clean energy, sustainable energy, energy that doesn't harm the environment. Efficient design can reduce resource use, better materials, smarter construction, more efficient systems, using less, doing more. The solutions exist. The technology exists, the will exists, we just need to apply it, to use it, to make it happen. Now let's think about the future. What will the internet look like in 10 years, 50 years, 100 years? How will data storage evolve? What new challenges will we face? The future is uncertain. But we can prepare, we can plan, we can innovate, we can adapt. Future generations will inherit our choices, the infrastructure we build, the systems we create. The problems we solve, or don't solve, we're building their world, today, right now. What kind of world do we want to leave? One with unlimited data storage? One with sustainable systems? One with balanced growth? That's up to us. Our choices matter. But here's something hopeful. Humans are adaptable. We're creative. We're problem solvers. We've faced challenges before. We've overcome them. We'll overcome these too. The data storage challenge is big, but so are we. So is our capacity to solve problems. So is our ability to innovate, to adapt, to thrive. The key is working together, individuals making choices, companies being responsible, governments supporting innovation, scientists researching solutions, engineers building systems. All of us. Together. Because this isn't just a technical problem, it's a human problem, a societal problem, a global problem, and it requires a global solution, a human solution, a collaborative solution. So remember this. The data storage challenge is real, it's significant, it matters, but it's also solvable. We have the tools. We have the knowledge, we have the ability. We just need to use them, to apply them, to make them work, to solve the problem, to build the future, together. Let me tell you more about what data means. When you take a photo, you're not just creating data, you're capturing a moment, a memory, a piece of your life. When you send a message, you're not just creating data, you're communicating, connecting, sharing. Data represents human experience, human knowledge, human connection. It's not just ones and zeros. It's us, our lives, our history, our culture. Think about what we're storing. Family photos, graduation videos, love letters, scientific research, historical records. All of it becomes data, all of it needs storage, all of it matters. But here's the question: what happens if we lose it? If storage fails, if data gets deleted, we lose more than data. We lose memories, we lose knowledge, we lose history. That's why storage matters. That's why this challenge matters. It's not just about technology, it's about preservation, about memory, about what we're leaving behind. Now let's think about balance. The data storage challenge reflects bigger questions. How do we balance growth and limits, innovation and sustainability, progress and responsibility? It's like riding a bike. Too slow and you fall over, too fast and you crash. You need balance, the right speed, the right pace, the right approach. We need innovation, we need progress, we need to keep moving forward. But we also need limits, we need sustainability, we need to be responsible. Finding the balance is the challenge. The data storage challenge connects to other challenges. Climate change, resource use, environmental impact. They're all related. All connected, all part of the same bigger picture. Data centers use energy, lots of energy. That energy comes from somewhere, often from fossil fuels, creating carbon emissions, contributing to climate change. Building data centers uses resources, materials, land, water, all finite, all limited, all part of the environmental impact. So solving the data storage challenge isn't just about storage, it's about energy, about resources, about the environment, about sustainability, about the future. But here's something important. We can solve these challenges together. We can innovate sustainably. We can grow responsibly. We can progress thoughtfully. Renewable energy can power data centers, solar, wind, hydroelectric, clean energy, sustainable energy. Energy that doesn't harm the environment. Efficient design can reduce resource use, better materials, smarter construction, more efficient systems, using less, doing more. The solutions exist, the technology exists, the will exists, we just need to apply it, to use it, to make it happen. Now let's think about the future. What will the internet look like in 10 years, 50 years, 100 years? How will data storage evolve? What new challenges will we face? The future is uncertain. But we can prepare, we can plan, we can innovate, we can adapt. Future generations will inherit our choices, the infrastructure we build, the systems we create. The problems we solve, or don't solve, we're building their world, today, right now. What kind of world do we want to leave? One with unlimited data storage? One with sustainable systems? One with balanced growth? That's up to us. Our choices matter. But here's something hopeful. Humans are adaptable. We're creative. We're problem solvers. We've faced challenges before. We've overcome them. We'll overcome these too. The data storage challenge is big, but so are we. So is our capacity to solve problems. So is our ability to innovate, to adapt, to thrive. The key is working together, individuals making choices, companies being responsible, governments supporting innovation, scientists researching solutions, engineers building systems. All of us. Together. Because this isn't just a technical problem, it's a human problem, a societal problem, a global problem, and it requires a global solution, a human solution, a collaborative solution. So remember this, the data storage challenge is real, it's significant, it matters, but it's also solvable. We have the tools. We have the knowledge, we have the ability. We just need to use them, to apply them, to make them work, to solve the problem, to build the future, together. The future of data is something we're all creating. Every photo we take, every video we watch, every message we send, we're all part of it, we're all building it. Together. Every choice matters, every action counts, every decision shapes the future. We're not just passive observers, we're active participants, we're builders, we're creators, we're problem solvers. The data storage challenge is big. But so are we. So is our capacity to solve problems. So is our ability to innovate, to adapt, to thrive. Together we can solve this. Together we can build the future. Together we can create solutions. That's the message, that's the hope, that's the future. Together we can solve this. We can build the future, we can create solutions. Together. And that's powerful, that's hopeful, that's the bigger picture. We're not just storing data. We're preserving memories. We're saving knowledge. We're building the future, one bite at a time. Outro. We've traveled through a digital journey tonight. From the data explosion happening every second, to the hidden infrastructure storing it all, to the limits of storage capacity, to what happens when those limits are reached, to the race to find solutions, to the bigger picture of what it all means. It's been quite a journey through the invisible world of data, through the physical infrastructure that makes the internet work, through the challenges we face, through the solutions we're developing, through the future we're building. We started with a simple question: how much data would it take to paralyze the internet? But that question led to bigger questions, deeper questions. Questions about limits, questions about solutions, questions about the future. We discovered that we're creating data at incredible rates, faster than ever before. And that rate keeps accelerating. Every photo, every video, every message, it all becomes data, it all needs storage. We explored where that data lives. In massive data centers, connected by undersea cables, stored on servers, using real resources, real energy, real infrastructure. The internet isn't magic. It's physical. It's real. We learned about storage limits, physical limits, technological limits, energy limits, cost limits, real boundaries, real constraints. Storage can't grow forever. There are limits, and we're approaching them. We imagined what happens when storage fills up. Systems degrade, services fail. Society is impacted. The consequences are real. But so are the solutions. Scientists are working. Engineers are innovating. Solutions are coming. We explored the race to keep up. New technologies being developed, better methods being created, smarter systems being built. The race is on, and humans are running fast. Finally, we saw the bigger picture, what data really means, what we're really storing, the balance between growth and sustainability, the future we're building together. The journey has been fascinating. We've explored the invisible world of data, the physical infrastructure that stores it, the limits we're approaching, the solutions we're developing, the future we're creating. We've learned that data isn't just numbers, it's memories, it's knowledge, it's history, it's us. And storing it isn't just about technology, it's about preservation, about memory, about what we're leaving behind. We've discovered that storage has limits, real limits, physical limits. But we've also discovered that humans are problem solvers, that we're working on solutions, that we're innovating, that we're adapting. The data storage challenge is significant, but it's also solvable. We have the tools, we have the knowledge, we have the ability. We just need to use them, to apply them, to make them work. The data storage challenge is real, it's significant, it matters. But it's also solvable. We have the tools, we have the knowledge, we have the ability. We just need to use them, to solve the problem, to build the future. Technology is powerful, but it has limits. We need both innovation and responsible use. Every choice matters. In building our digital world, in shaping our future, in preserving what's important. The future of data is something we're all creating, together. One bite at a time, one choice at a time, one solution at a time. As we move forward, we'll face new challenges, new limits, new problems. But we'll also develop new solutions, new technologies, new innovations. The race continues. The challenge evolves, but so do we. The key is staying aware, understanding the challenges, working on solutions, not panicking, but not ignoring either, taking action, making choices, building the future. Together we can solve this, together we can build the future, together we can create solutions. The data storage challenge is big, but so are we together. Thank you for exploring this digital journey with me tonight, for thinking about these questions, for being curious, for wondering. That's how problems get solved. That's how the future gets built, one question at a time. Curiosity drives innovation. Questions lead to answers. Wonder leads to discovery. By thinking about these challenges, you're part of the solution. You're contributing to the future. You're building something amazing. If you found this exploration interesting, if these calm thoughts help you unwind, consider exploring more. There are endless questions, endless mysteries, endless wonders waiting to be discovered. The digital world is full of mysteries. How does artificial intelligence work? How do quantum computers function? How will virtual reality evolve? Each question leads to more questions. Each answer reveals new mysteries. The journey never ends. The wonder never stops. The digital world is vast, complex, fascinating, and you're part of it, every moment, every day, creating data, using data, shaping the future of data. It's a responsibility, but it's also an opportunity to build something amazing, together. As you drift off to sleep, think about the digital world around you. Think about all the data flowing, all the storage working, all the infrastructure supporting. It's incredible, it's complex, it's fascinating. And you're part of it. Every moment, every day, creating data, using data, shaping the future of data. Your choices matter, your actions count, you're building the future, one bite at a time. I'm Sleepy, and this was your science story for tonight. Sweet dreams, and keep wondering about the digital world around you. It's more fascinating than you might imagine. And you're part of it. Every moment, every day. Building the future, one bite at a time. Remember, every photo you take, every video you watch, every message you send, it all becomes data. It all needs storage. It all matters. And together, we're building the future, one bite at a time. The data storage challenge is real, but so are the solutions. So is our ability to solve it. So is our future. Together we can solve this. Together we can build the future. Together we can create solutions. Sweet dreams. And remember, you're part of something bigger, something amazing, something we're all building together, one bite at a time. As you drift into sleep, let your mind wander through the digital world, through data centers humming with activity, through cables carrying information across oceans, through servers storing memories and knowledge. It's all connected, it's all working, it's all part of something bigger. You're part of this digital ecosystem. Every photo you take becomes part of it. Every message you send flows through it. Every video you watch is served by it. You're not separate from it, you're part of it. You're building it, one bite at a time. The data storage challenge is real, but so is our ability to solve it. So is our future. Together we can solve this. Together we can build the future. Together we can create solutions. Sweet dreams, and remember, you're part of something bigger, something amazing. Something we're all building together, one bite at a time. The future is bright, the solutions are coming, the race continues. And we're all in it together.